Good afternoon, everyone. I'm Hakan, and I'm here to talk about mobile application quality today. And I want to share our story at Delivery Hero about how we defined a single metric for measuring our mobile application quality, which is called Application Quality Score, and in short, we call it AQS. And we are using it for about 2 years now to systematically improve and maintain the stability and performance of all our DH mobile applications. And in the first part of the talk, I will explain the motivation behind creating a technical quality metric, and then, and also how we defined it in our own way. Then we'll be focusing on the improvement journey of our riders' app stability and performance. So before diving into the technical topics, to understand the why behind this journey, let me provide the context about Delivery Hero scale. Delivery Hero is present in around 70 countries, and its mission, the main mission, is to deliver anything straight to customers' doors, and its main business is food delivery. And we operate with 11 brands and with more than 40 mobile applications, which supports 47 languages. And Delivery Hero processes over 10 million orders per day, and at this scale, you can imagine even 0.1% degradation in app stability or performance can affect tens of thousands of users, and it can have a huge impact. So after giving a brief introduction about Delivery Hero scale, maybe let's start talking about technical application quality, as we promised. And we'll be exploring several practical cases about quality in the upcoming parts of the presentation, but before that, let's start a bit formal and define the technical application quality as a term. So here is an opinionated definition of mobile application technical quality. Let's maybe read it together. It's a short one. The technical quality of a mobile application is a quantifiable measure of its underlying performance, stability, and resource efficiency, which collectively determine its reliability and responsiveness from a user's perspective. And the next part is, I think it's also quite important. It measures how well the app is engineered and maintained on a technical level, and it's independent of its design or feature set of the product. So we will be digging into these details of these pillars in the next slides. So let's start talking about maybe first if technical quality has any impact on the business. We had a formal definition, and let's try to answer this question now. So a slow or buggy app creates a frustrating journey for users, making even a feature-rich product feel clunky or unreliable. It's a top reason generally for app uninstalls. And a decrease in stability and performance can lead to a spike in user churn and driving customers most probably to your competitors. Also, negative experiences lead to bad reviews in app stores, and which directly hurts your app's reputation and visibility, preventing new user acquisition. And also, a lack of trust in your app due to instability makes users far less likely to make purchases or subscribe to your premium plans, for example. And the last one may be the most important one. When stability and performance issues get out of control, teams generally just stop all feature development and they enter firefighting mode and draining your resources and disrupting your product roadmap. So in short, I think we can say lack of technical quality isn't just a technical problem, but it is indeed a business problem. So after talking some formal definitions and laying the ground, I think it's time to start talking about AQS. And around 2 years ago, in 2023, our engineering leadership started an initiative to assess all DH mobile applications' technical quality. And given this motivation, an AQS framework actually is proposed and by a group and accepted, and it has become a global standard starting from November 2023. Since then, it has become the metric that measures the technical quality of all DH mobile applications. After AQS framework is announced, the expectation from all mobile app owner teams at the same time is set to reach and maintain the quality targets that is mandated by the framework. And yeah, let's get into details of this framework. So AQS targets all mobile applications in Delivery Hero, including customer, vendor, and rider mobile applications. It's platform agnostic. It targets Android and iOS. It's independent from technology as well. You develop in Flutter, KMP, native. It doesn't make any sense, any difference. And it is a single number in the end, just one single number between 0 and 100 that is calculated based on these three pillars that I mentioned before as well. So in order to calculate application quality score, this framework defines three elements. These are metrics, weights, and targets. We'll be detailing these elements in the next slides one by one. So let's first start with the metrics that contributes to AQS. So first metrics are crash-free users, ANR, application not responding. Maybe if you are using Google Play Vitals, you will be actually familiar with those. And the definitions are also coming from there. But we are mainly interested in the user-perceived crashes and user-perceived ANRs because AQS is all about user experience in the end. And the next, by the way, ANR is Android-specific, but to support other platforms, of course, iOS, the counterpart of ANR is hang rate there. So there are some small changes like this in the definition, but the aim is the same. The objective is the same. And the next metric is app start interactive time. And it measures the time from clicking the app icon in the launcher till any destination screen, like home screen. It's not the splash screen, but your target screen, home screen, or your login screen is loaded and became interactive. And there is this core screen time to interactive metric. It's a bit different from others. So here you need to define core screens for each application. Generally, core screens are the screens which are part of the critical flows of your app from business perspective again. For example, for customer apps, they are the screens in order flow. For rider apps, they are the screens which are on the login and delivery flows. So, yeah. And the next two metrics are related to screen rendering, and these are also adapted from Android Vitals, the definitions. And the next one is the app size, and it's the compressed size of the app downloaded by users at install time. As I mentioned, we try to align with Android Vitals, but generally we tweaked a bit for iOS while adapting to iOS, also even while adapting to Android. And we defined the metrics that contribute to AQS. Now, in order to calculate single number out of these metrics, we need to define the weights. And as defined in the quality definition slide in the beginning, we have three pillars, performance, stability, and resource efficiency. And here, you can see the distribution of our metrics into these pillars as follows. And let me also show the weights, which needs to add up to 100, of course. And here you can see. I want to highlight actually three things here. Let's go one by one. The first one, maybe you will see like stability is like 60%. Why you are actually allocating that much of weight to this one? Because without having a stable app, making it performant will not make much of a sense in most of the cases. That's why we prioritize stability over performance for rider applications. And there are some small tweaks for other applications. For example, for customer apps, it's 50%. And the second point that needs a highlight could be why app size is not contributing that much. To be honest, it was a bit challenge for us to come up with a general recommendation for all these 40 applications, because each app actually has its own constraints, and they are being used in different circumstances. For example, in restaurants, riders are using on the way, people are using generally from their homes, and etc. So we couldn't find a generalization here, but we still wanted to give a weight to it so that everyone also invests reducing their app sizes. And the last point is that resource efficiency pillar, maybe you'll see, okay, just one metric there. We explored other parts more than this one. We are also planning to entertain an idea to include memory, network usage, and battery consumption later, but these are not the part of guidelines as of now. So these will be upcoming topics. So now we have metrics, weights, but we are still missing one more element, the core one. It's targets. So here we are defining acceptable and ideal targets for each metric so that we can estimate how good we are performing for each metric. Acceptable level is the midpoint of scoring scale, while ideal value is the number that will bring the top score for that individual metric. You start getting a score after this red region, red, and then in orange, you will be like, okay, getting some score, but that score is still not acceptable. And if you reach the acceptable one, okay, it's unacceptable, but you still have some room for improvement until ideal value. And beyond ideal value, your score doesn't change, you get the full score, and you stay there. But you can, of course, create some buffer for your sake. And let's get into concrete numbers about these targets. Let me give all of them together here. So as you can see, for crash-free users, for example, our ideal value is 99.9%, and acceptable value is 99.7%. And this is user-perceived crashes daily. And our riders are working 5-6 hours per day. So one day is like a lot of sessions for us, but this is the target that we have. So every day we are expecting from 1K riders, only one crash can happen. And you can see the scale here, just use the same scale, and then if you put it here, after 99.5% for crash-free users, you will start getting some score. And then the acceptable value is in the mid, as I said. Yeah, depending on the weight that I showed in the tree, the score will be the top score that you can get. So for example, for crash-free users, it's 35. And yeah, let's come to this most exciting part. Now we laid the foundation and we know how to calculate AQS. And I think it's time to answer this question. How did we start? What was our initial AQS score? And to be honest, it wasn't a clean start for us. And let's move on to the next slide and see the picture. There's not that much to see, but yeah, our journey with AQS began in November 2023. That was the time actually we got this picture. From stability and performance, our score was 0. And we just had some score from app size, as you can see here, and that's all. So the initial data showed us something undeniable, and there was actually a big room for improvement here, and this was our actually wake-up call. At that time, we immediately actually, after having this clear picture, we immediately started to find a strategy to overcome this situation. And of course, we couldn't fix everything at once. It's not just one metric we are failing, so we break our approach down into 3 phases: now, next, and later. And the first priority was to stabilize the app by fixing our most critical issues. We focused on the big things that were causing actually our users the most pain, major crashes and major ANRs. And after having an acceptable level of stability in our app, we plan to move to the next phase, which is performance, mostly. And this was about going deeper, as I said, into performance. First, since we don't have why our app start interactive, for example, is not that good, we started to collect performance data with a lot of traces by instrumenting our app using Firebase Performance and Sentry. And we could understand the root cause. Then we were able to understand the root causes, which operation is taking longer, why do we have these issues. From there, we prioritized improving App Start Interactive, core screen TTIs, rendering performances, etc. And finally, if this is still the strategy we will apply later, but we were also thinking like if we improve our AQS into some level, if we don't invest later, then it will come back to the position that we had before. So our long-term plan is to ensure this doesn't happen again. So we'll regularly review our AQS and keep teams accountable to the targets we set. We'll be building systems, for example, to early detect regressions. I will be also talking about this one. And the ultimate goal is to, of course, not stay in the acceptable level, but go and push for the ideal values and maintain a high standard. So we've seen our strategy. Now let's see if we were able to apply that strategy or not. This next section will be like improvements deep dive. So we are going to walk through each of these metrics one by one, and I'll try to show you exactly what actions we took. Not all of them, of course, but these are just the highlights. And let's start with the metric, actually, that has the biggest weight. It's crashes. And so while our process gave actually us a clear roadmap, the journey to fixing crashes was far from simple. We faced some major challenges that were difficult to solve. And the biggest issues fell actually into three main categories, I can say. So first one is tackling with third-party SDKs. Our rider safety SDK, I will not name any SDKs here, but it's just rider safety SDK, security and fraud SDK that we are using, and the map provider that we were using. We had a lot of challenges when it comes to crashes. And the next one, maybe this is everyone's pain, I don't know, but running services with restrictions, since we need to collect location information of our riders while they are moving, and we had a lot of limitations in different devices, and your service is being killed. So there are a lot of crashes as well when you're trying to start service at some point. And in every Android version, these restrictions come more strict, as you know. And also Android OS support. We were supporting like Android 5, 6, 7. And then now we are supporting Android 8 and above. And the previous versions, like 5, 6, and 7, for example, had much more crashes than the others. So also this helped us. And also device quality. So since we are operating in like 70 countries, the quality of devices in, for example, in Africa is not the same that's like in Korea, for example. So, and the last part, I think this needs a dedicated section itself, Compose bugs, because we started very early adopting Compose, but we accepted to fight with some instability, crashes, and etc. I will also actually tell a story about this one soon. Yeah, even let's start with that one. This is the highlight for the crash from Compose. So one of our biggest challenges, as I said, was with Jetpack Compose text fields, as I mentioned in the previous slide. So when we first started using Jetpack Compose, the initial versions of the text field had several major bugs. I don't know, maybe you also faced this one. Focus was not working fine when you were actually interacting with keyboard. There were several issues reported in Google issues. So we just wanted to continue using Compose everywhere, but if you don't have text fields, how we can do that? So we used interrupt solution as a mitigation. So from system view using text view, and it worked for a while. And then we just updated our Compose version at some point, and our mitigation solution with interrupt started to break dramatically. And in some devices, only in some devices, it was crashing a lot. And then we couldn't update our Compose version for a while. And the solution actually came, not from us, but Google. Google actually fixed those bugs, crashes, and other stuff in some stable version. And then we immediately actually go back to Compose, using Compose text fields. And then our app stability become a better level. Since then, actually, yeah, we have perfectly fine working text fields, let's say. And yeah, but it took almost 1.5 years to remove all the crashes from text fields. So Every time we bump up the compose version, there were always a problem with the text wheels, but now they are solved. And I think Google also recognizes, because in the beginning of the compose, there was a lot of instability issues and other stuff with the library, let's say. And Google recognized the issues that are reported by Android community and has since made actually massive investments to ensure compose is more reliable. And these are from actually an article that they recently published, maybe 3-4 months ago. I will also provide the link here. So they invested actually in intensive internal testing, and they are testing all in their internal applications before actually releasing to everyone. And also better API service. There was like a lot of experimental APIs. Then now they are committed to removing them and make them stable. And also improved debugging. Now you have more tools in Compose to collect more information before actually going in production. And also in performance, they had a lot of actually improvements. I wouldn't mention all of them, but here I want to show a picture. This is from that article, and you can see how performance jank rate is actually promised to be reduced by just updating your Compose version. And this is, of course, for an internal application. They are benchmarking, but you can find more information in this link. So the later version of the Compose, the latest version of the Compose, we can say is much more performant than the ones 2 years ago, and also stable. So now, yeah, when it comes to app freeze, app is not responding, actually this can be in 3 different, let's say, scale. So let's try to actually first make this differentiation. So it's all about main threads when we say freeze, stutter, or something else. So there are 3 metrics that are related to this. So these are slow rendering, frozen frames, and ANRs. So, but they are actually generally interested in the main thread in different scales. So let's first check what slow rendering is mainly. This is generally the most minor issue if you check these other 3. The app can't keep up with the display's refresh rate, leading to dropped frames and a janky user experience, especially during animations or scrolling. And it's a performance issue that's noticeable, but often from user's perspective, it's recoverable in the end. Frozen frames, this is a much more severe issue. Here, a single frame takes an excessive amount of time to render, and the UI appears completely stuck or unresponsive for nearly a full second. And from a user's perspective, the app looks like it has frozen, hung. It's a significant negative user experience that breaks the flow of interaction, but app still kind of works. And the last one, when it comes to ANRs, and this is where actually performance becomes a critical stability issue. So the main thread is completely blocked for more than 5 seconds, causing the app to be completely unusable. And in most of the cases, this triggers a system dialog saying that, okay, giving the user only one option, force quit or wait. And waiting generally doesn't make any improvement. From a user's perspective, this is a catastrophic failure. Very similar to crash experience, to be honest. Yeah. So understanding actually these distinctions was kind of critical for us to prioritize and address the issues that were impacting our riders the most. So we are starting from ANRs. And in AQS as well, ANRs has 25% weight, frozen frames 13, and then slow rendering is 5%. It also shows which is more impact on the quality. Now let's talk about one of our biggest aha moments, I can say, on this journey, what we call the ANR ripple effect. We realized that a lot of our ANRs, which appeared to be separate issues, were actually connected. So the problem was that we had multiple distinct heavy operations all running on the main thread, while each of these tasks might have been individually okay, their combined cumulative delay was enough to push us past the 5-second ANR threshold. And ANR tracking tools including Google Play, Firebase, reports each of these incidents as a separate ANR because when this happens, the stack trace will be different in most of the cases. Because which operation was at the end of this 5-second bucket actually will report its stack trace. This led us to underestimate the true impact of the underlying root cause as we were trying to solve multiple different ANRs when the real problem could be a single or a couple of issues. We discovered that by just solving some of these major underlying issues, we could free up a significant portion of the main thread's time. This provided enough breathing room for the remaining operations that were also contributing to other ANRs before, and they became less visible. The result was a much larger drop in our overall ANR rate than we expected, because fixing one ANR had a positive ripple effect across many others. So if you solve one ANR, actually you are not solving one ANR. But if you are solving one crash, you are solving one crash, a single crash. This is the difference, and there's a ripple effect between these ANRs. While the ripple effect was a good insight, we still face significant challenges with ANRs, and we realized these issues fell into two main categories. And the first part, of course, is first part of the ANRs. These are our own ANRs. We found out that our app was performing heavy operations on the main thread, database operations on main thread, eager dependency injections when our application is created, startup initialization in main thread, and the root cause was actually a fundamental issue. We were doing too much work on the main thread, and often not at the right time. I think this part is critical. And this we need to address. And the third party, of course, it's also there for ANRs, and it's the biggest chunk, to be honest. Just like with crashes, we found that many ANRs are coming from third-party dependencies, including our rider safety SDK, again, map provider, security one as well. We also saw issues with our use of Firebase performance library and shared preferences. I will also actually explain it like a story soon. Let's go and highlight the first one. This is related to ANRs. So we'll talk about how our app's performance and stability were suffering, but some of those issues came from an important area. It's from security. For us, this became a tightrope walk, balancing essential security with user experience. So security SDKs are essential for our business, but their heavy tasks can lead to a sluggish app and increase the risk of ANRs. So these checks, the ones that are injected by security SDKs, for example, which include things like cryptographic operations, file system checks, code integrity scans, all require valuable CPU time and can block the main thread. So we kind of learned it a bit hard that more security isn't always better. Having more checks than needed often doesn't bring additional value. So every check comes with a cost. Even if it's running, they promise to run it on a background thread, but they still access shared system resources. And too many of them can lead to a blocked main thread causing an ANR. And the solution was, it wasn't about removing security, of course, but about being smarter on it. So first, we learned to configure our security checks so they provide a good level of security without making the app unresponsive. And second, we took a hard look at our security requirements and began to determine our security needs and address only those. So finally, we now monitor our performance of security checks and iterate on our configurations in every release. And we try to find the optimal balance between security and user experience. So there's another deep dive related to application not responding issues, and this is related to Firebase performance and shared preferences together. Let's dive into this one. And maybe, most probably, you've seen the wet holding logs, F-Sync ANRs. If you check your Google Play Vitals or Firebase, you will see most probably this type of ANRs there. And there could be several reasons of this. Actually, one of the issues that I will mention will fix maybe some of these, but these ANR's reasons could be very fragmented because of different reasons. As you can see, there is actually an ANR stack trace from Google Play Vitals here. There are 2 threads, and the first one, the main one, says, actually, I'm waiting thread 39. And if you go to thread 39 stack trace and check what it is doing, actually it's trying to write to something to shared preferences, and then it's waiting for some luck. But why main thread is waiting this thread? Let's check that a bit in detail. To understand the core issue, we need to understand this queued work, because there is this, the main thread actually is waiting on queued work process pending work. Let's go into details and understand what queued work is doing. When an activity is paused, Android's queued work class processes any pending work, which intended to run on background threads, including the pending works, all these in background thread, are being actually executed in a sync manner. In the background thread still, but main thread waits all of these to complete in a blocking way. So, for example, you set shared preferences.apply. I'm not saying commit, you are saying apply, and then it's scheduling a background task to write it to file, shared preferences file. You are saying that, okay, it will run in background, it cannot have an ANR, but that's not the truth. This is being actually sent, but queued work keeps a reference to this task. If it's not completed when activity is paused, then this is executed immediately. If you have, for example, 20 shared preferences right there, it will write them in background thread, but main thread will wait it on pause, and there will be an ANR, most probably. So in our case, we actually find out this, and then just try to understand which actually shared preference write operation was causing it, because there are several reasons, several usages of shared preferences from several places. So we checked, and we found out that we clicked our application icon in launcher, we reached our home screen, and we have 1K shared preferences.apply calls. And out of these, 800 of them were coming from Firebase Performance Library. And activity is paused. Maybe you open home screen and then just go to another app, and your activity is paused. And at this moment, queued work is just taking into action to save shared preferences, because it wants to be on the safe side that it will be persisted, because it's the contract of shared preferences. And then you have actually ANRs, right? Because your main thread is blocked, waiting some other background tasks to be completed, and you stay there most probably more than 5 seconds in some devices, in some conditions, then you get ANRs. So how actually we fixed kinda this issue partially? Of course, we reported the issue. It took a couple of months to actually persuade that this is an issue, and then the issue is kinda solved partially. And now our calls actually reduced from 800 to 100, kinda, still coming from Firebase Performance Library. And here maybe you can expect that, okay, I will say do not use Firebase Performance, but I wouldn't say that. I will say do not use shared preferences, even with apply. Apply doesn't make things better, and even it can make it worse in some cases, as I mentioned. So, of course, data store is not one-to-one replaceable of shared preferences, but you can use data store, room, maybe some other persistent library for your use cases, and stick to shared preferences only maybe for very small operations or some small data, I would say. After this interesting 2 stories from maybe ANRs, let's switch to App Start to Interactive. And a fast app start is a must-have, and we approach it with a systematic 6-step methodology to actually, first we need to identify, right? In App Start Interactive Flow, this is the first challenge. So you don't have stack traces submitted to somewhere else. For ANRs, for crashes, you have it. But for this one, you need to collect it in the beginning. So we collected it through Firebase, and we had a lot of subtraces. That's our Firebase performance usage. And then we profiled it afterwards, checking with Android profiler, with the help of Perfetto, we find out which actually operation is taking longer and when. And then we devised like some actions. The first action was like remove it if it's not needed. I think this is the easiest solution. If you don't need that operation in your app start flow, just remove it. Defer it to somewhere else. And if it's SDK related, report to them. And if it's on your own, yeah, take care of it. So then we also, before even releasing, we are benchmarking it with a tool that's called Regresso. This is an internal one. And we check all these traces. Is there any deviation between these traces? Commit to commit, release to release, we can check these changes. And generally, we also guard it with some feature flags so that we don't have any other regressions while trying to fix something. Maybe we can break other things as well. So here, I just want to actually visualize, for example, a scenario. You added a lot of traces in your app start interactive flow and checked which operation is taking how much time. And then this is, let's say, this is your first snapshot. Then actually you notice that operation 3 here was not needed in this app start interactive flow. Actually, when I remove it, I saved half a second here, right? Then, after checking in detail, I saw that, okay, 1, 4, and 5, these operations can be offloaded to background tasks, and they can run in parallel. But however, here, operation 2 is kind of depending on one of these, and then you need to execute it later. So after rearranging these operations with better utilization of resources, we kind of end up with 2.5 seconds, which is kind of half of the second that we had in the beginning. And what we did here is just rearranging things. We didn't even improve anything in individual these operations. So just rearranging can even make your app start to interact with better. This is better resource utilization. So after actually analyzing app start interactive flow, and here are our actually main findings. And these are sequential initialization on main thread. On upgrade, we found this is happening a lot. The second one is eager dependency injections on main thread. And the last major issue that I want to highlight is about baselines and startup profiles. If you just record your core flow and has baseline and startup profiles for them, it will definitely improve your app start interactive flow, and it helped a lot for us. Let me just talk about this sequential initialization. You have your application class, and there you have X init, Y init, Z init, a lot of initialization in sequence. But you can, if they are initializable, let's say, in background thread, I think you can do it in this way. Just one interface, and then this app startup manager, for example, collects all the things that wants to be initialized when your application is created, and then you can just initialize all of them in a background thread in parallel. So now they are not sequential, and you actually solved a big problem, and it was like here, right? We did it here as well. So the next one, this is a bit more interesting. Async dagger injections with provider and lazy. So the problem here is that creating some dependencies might be very costly, like OK, HTTP client, JSON, and dagger by default, since it's starting from main, injects everything in main thread. And this might contribute to ANR, and in our case, it was actually doing a lot. So the solution here is not straightforward. So what we did, we defer actual dagger injections by lazy and provider, and call get functions of lazy provider injections on a background thread. So initial construction of that class is being done on the background thread. And we also make sure that costly dependencies are not created on main thread. Let me go to the next slide to show how we can make it work. So left side is the same. We are utilizing it for initializing JSON initializer. And as you can see here, the init function is just calling get, and this function is being called inside app startup manager. So it's running in background, and you are saved. So I think it's a good point to mention one more thing here. Maybe I showed an example of JSON, but for Android, it's not the best serialization library, and JSON library is actually repo. clearly mentions that you do not use JSON because it uses some reflection, which is not good. For Android, there are several reasons. Kotlin serialization or Moshi, some other libraries could be much better than this. And for improving frozen frames and slow rendering, what we have a methodology. First, we find screens with rendering issues, Firebase performance, Sentry, and then we deep dive with profilers, as I mentioned before as well, and we fix the issues. And here are the issues, actually, that we fixed generally by applying this. Using async image loading in Compose. You can use coil, for example, for this one. Otherwise, all the images will be loaded in main thread. Unnecessary animations, if you have them, talk to your designers and let them remove. And simplify vector images with Avocado. Generally, designers provide very big files. You can simplify them. Migrate from PNGs to WebP if you want to still use raster images, and then you can do this one. Also use latest version of Compose because of that chart I showed you before. So another deep dive could be using dispatcher IO by default in vModels to increase your better frozen frame metrics or slow rendering. But Sinan yesterday had a talk and detailed this, so you can check that one. I will just skip it for the sake of time. So the interesting part, I'm approaching to last. So what we achieved in 1 year, let's check. This is the first half. From 0, actually, we came to 56.5. And our strategy was to go with stability first, crash-free users, ANRs, they are kind of good state. F-Start Interactive, core screen, TTS, and frozen frames, we had some scores. And our F-Start Interactive, it was 15 seconds, now it came to 5 seconds. So it's quite good for us. And then in the second half of the year, we even pushed further, and then we have a huge jump in our core screen TTIs, F-Start Interactive, because our focus was more on performance here. In the end, we kind of applied our strategy and became from 0 to 70 in 1 year. So our strategy worked here. So what are we going to do to keep our application stable and push for ideal numbers? So Regresso is our tool. For performance traces, we just detect regressions using this tool, commit to commit, release to release. We set up automated alerts, and our on-call engineers, for example, if something goes with crashes wrong, they are in real time alerted. And we are trying to extend it to other metrics as well. And we have monthly application quality reviews in Android chapter, in iOS chapter, and we review our applications and then prioritize actions for the next month. And teams actually work on that in this month, in their teams. And as a result of these reviews, we delivered more than 200 tasks in the past, actually, 1.5 years. So what's next? Let me make it quick. So we are actually developing TH performance SDKs, and it will actually unify reporting. We are integrating actually with web views, so core screen performance of web views will also contribute. We will have AQS by device quality, low, mid, high-level devices and their expectations, and we are continuously refining our AQS targets every year. So this is the last slide. Sorry for taking more time. And key takeaways, I can say, define a technical quality metric that makes sense for your product. It doesn't need to be AQS. You can define your own application quality metric and make it visible with the support from your engineering leadership. I think this is critical, otherwise you will not have a room to work on it. Set quarterly, monthly targets for your technical quality and make it part of your roadmaps. I think this is also very critical. And then review your metrics regularly and take actions to improve the quality. So that's all. Thank you for listening.